Well, welcome everybody to GeoHug. So I'm very excited that we've got Carl Spandler joining us today. But before we do get stuck into today's session, I'd like to take this time to acknowledge the traditional lands which we're all coming from today. I live on the beautiful lands of the Gadigal of the people of the Aurora Nation. And I'd like to pay my respects to the elders past, present, and future. And yes, I am very excited that we have Carl Spandler joining us today. So Carl is a professor of geology in the Department of Earth Sciences at the University of Adelaide. He uses petrology and geochemistry to research the evolution of the Earth's crust and mantle and the formation of metalliferous ore deposits. So his current research focuses on understanding the how, where, and when ore deposits of critical metals, such as rare earth elements, are formed in the Australian continent. And it's going to be brilliant hearing from him today about novel in situ methods applied to ore deposits, a game changer for resolving the temporal evolution of mineral systems. So this is going to be a fantastic session. I hope you all enjoy it. I'm going to be promoting you up as panelists, so please don't be shy. If you're able to come on through, you can get your cameras on, get your mics on. We'll start up some awesome discussion at the end. But yes, thank you so much, Carl, for joining. It's amazing having you here today.
Oh, you're welcome, Jess, and it's great to be here.
It's brilliant. I was, before we do start, I was, very curious what got you into geology to begin with.
I think it's probably not so different from how a lot of people got into geology, which is probably in first year, taking first year geology at uni as a sort of an extra subject, you know, being generally interested in science.
Yeah.
And seeing that it's just a great field that gets you out in the bush and out and seeing landscapes, and great for traveling, and I think it was hooked from there, basically.
Yeah, that is a really common way that a lot of people do get into it. And I imagine you have traveled a whole heap with your role. What have been some big career highlights for you?
Yeah, you're right. It's the travel for sure, I would think.
Yeah.
Which is you know, you hear a lot from physicists and chemists that the thing that they really are jealous of us about is the fact that we get to see so many cool places. I think for me, places like I did a postdoc for 3 years in Bern in Switzerland, so I spent a lot of time working in the Swiss Alps.
Yeah.
And I've got a rock to show you from the Swiss Alps in a moment. But also all sorts of different places that I've travelled, all through strange parts of Australia that the general public never gets to see.
Yeah.
So I think it's been really lucky in that regards.
That's amazing. And yes, I'm very excited to see what pet rocks you have bought for us today. So let's get straight to that part.
Yeah, okay. So I guess I've got 3 rocks I was going to show, and they sort of do span a little bit of the research I've done over the last, whatever it is, 30 years or so.
Yeah.
And I guess at the moment, my research focus is mostly around critical minerals, understanding how and where they occur in concentrations in the Earth's crust so we can find more deposits of it. But earlier on, when I was doing my PhD, I was initially working on much more in geochemistry, petrology, particularly of high-pressure metamorphic rocks. And that was my PhD topic in New Caledonia. And then that took me to a postdoc in Bern, where I worked on high-pressure rocks from the Alps. And so my first rock I've got to show you is this one here. It's quite large.
Oh.
But this is quite a famous rock, actually. This is from the Italian Alps. And it's, as you can see, it's quite shiny. It's full of muscovite and white minerals. It's called a white schist. So this is the Dora Myra white schist, quite famous locality. And it's spectacular because, well, it's weird because it has a very weird composition. So metamorphic rocks, they're usually just metamorphosed mafic rocks or basalts or sediments. This composition of this rock doesn't really match any unmetamorphosed equivalent. Very magnesium rich, very potassium rich, very silica rich. It's full of muscovite. It's got talc, quartz, and you might be able to make out this thing here, which is pyrope garnets, giant magnesium-rich garnets. They get up to soccer ball sized.
Wow.
So it's a pretty spectacular rock. And this rock is particularly famous because the quartz, or inside these garnets, there are inclusions of quartz that are were coesite. And if you know what coesite is, it's a high pressure polymorph of quartz, only stable above about 26, 28 kilobars, which is equivalent to sort of 80 kilometers in the crust. And so the first person to recognize this, a guy called Christian Chopin, basically realized this rock comes from way deeper than we ever thought was possible for continental rocks to come. And that's how they then defined a new class of metamorphic rocks. Ultra high pressure metamorphic rocks come from that rock.
Wow.
So it's a pretty cool rock, really.
That is a cool rock.
Yeah, and we still don't really know how white schists form, actually, how they get their weird composition. But they are in continental rocks that have been deeply subducted, usually related to continental collision zones in the past.
Wow.
Yeah.
Wow. That's so interesting. Oh my gosh.
So that was my first rock. I can go to my second one now.
This is impressive. Keep going. Yes.
That's a weird rock. This is an even weirder rock. And I reckon not many people on the call would have actually heard of this one. It's this thing here. It's hard to pick it up on the camera, but it's sort of a distinctively pale green or browny tan colored rock. It's a rock called nunderite, and there is only one known locality of this on Earth, and that's just north of Broken Hill in the Mount Arrowsmith volcanics. And the rock itself, it's from a single outcrop, only a few meters in dimension, and it's been sort of quarried for, you know, they polish it up into little stones and they sell it in shops because it is a really spectacular rock. It doesn't really come out very well on the camera. But it's been a bit of a mystery of what this thing is. And we had an honours project here last year by a student called Luca Johns-Mead, who did a detailed deep dive into what this rock is. It's made up of agerine, which is the greeny mineral, and some feldspars and some zeolites, so naturalite, as well as a whole bunch of really weird minerals like schizolite, which probably most people have never heard of, and some strange zirconium, rare earth minerals, etc. It's really enriched in a whole bunch of these rare metals.
Wow.
And the results of that work has just been published in the Australian Journal of Sciences, is that we think it was a very unusual phonolite that has been then essentially altered and metamorphosed. And that's sort of significant because these really zirconium rare earth rich phonolites are quite rare, and they're good indicators for rare metal mineralization. So those environments where you get those, which is continental rift for the Mount Arrowsmith volcanics, about 580 million years ago that was formed, where we might go to find rare earth deposits, for example. So it itself isn't high enough concentration to be a deposit, but it's a good indicator there might be other things around in that part of the world, which is fairly underexplored at the moment.
Wow.
So
You're
that's none.
very good pet rock storyteller. I love this.
Yeah, I was trying to pick a few things that people mightn't have seen before. The last one I've got is stuff we're working on now. So we've got new projects working on lithium pegmatites. And we were lucky enough to go to Canada a couple of months ago and go to the Tanko pegmatite mine, lithium mine. And we've got a piece of this, which comes from underground in the mine. And again, the camera's not doing it justice, but you could probably pick out that purpley color there, which is lepidolite, so the lithium mica, and the sort of grey stuff in between. It's pretty dull really, but that is a mineral called polysite, which is a cesium zeolite, another zeolite, but it's a cesium mineral. And there's only about probably 10 or so known cesium minerals in the world. And that's probably the main cesium mineral and the main economic source for cesium comes from that mineral in pegmatite.
Oh my gosh.
Yeah.
This is awesome. Wow. I've learnt a lot today, so thank you for sharing all of that with us.
Yeah, that's okay.
Well, yeah,
Cool.
thank you. Yeah, it's so great to have you on today. I really appreciate you taking the time to talk to us. It's gonna be an awesome one. So yeah, if you want to share your screen and we can get stuck into
Okay.
it.
So the type, as you can see, title of my talk today is on geochronology and related to ore deposits. Although what I'm going to talk about isn't just related to ore deposits, but it is sort of my area of research at the moment, which is why I'm going to focus on that. You can see a big list of names here. These are all people from the University of Adelaide. And there has been a bit of a focus in the last few years here about developing these new tools for dating rocks in general, but particularly ore deposits. And so while I'm giving this talk, I've really had a fairly minor role in it. It's these other people listed here that are really the ones who have driven this research, particularly Stain Glory, the next name there, and Alex Simpson, who did his PhD on this, and I'm going to show quite a bit of his work, and Sarah Gilbert, who's really been the technical wizard behind all this. Without Sarah, a lot of this wouldn't have been possible at all, and we're very lucky to have her running our laser ablation labs here at Adelaide. So, I've in the title here, I've said the game changer for temporal evolution of mineral systems, and I think phrases like game changer and paradigm shifts, they get used all the time, and they're probably not that well justified in most cases. But I think in this case, and what I hope to convince you today is that it really is justified. This really is a game changer for geochronology. The other thing I want to point out here is down the bottom, we've got this logo here for the AIC Critical Resources for the Future Centre. This is a new centre that's just starting up. This is a bit of an ad. This whole talk's a bit of an ad, but anyway. But this is an ad for this new centre that's starting up. This is a AIC training centre for training PhD and postdocs. That's going to be led out of University of WA with ourselves at Adelaide as a partner university, along with UQ and ANU. And so we'll be launching that centre later this year. So keep an eye out for that. It's going to be everything to do with research around critical minerals, etc. All right, that's enough of an intro. So why, I guess geochronology is probably not the first thing that people think of when they think about what we need to know about an ore deposit. But I guess the point I want to make here is that we really need to know a hell of a lot about ore deposits. And if we're really going to be able to find these deposits that we need to provide metals, we're going to be needing to bring every trick in the toolbox to the table. And this, I guess, is just to sort of demonstrate how rapidly the situation is changing. I think up till sort of 20 years ago, that top list there is the main commodities that we would mine. It's not obviously complete by any means, but it's a fairly restricted list of elements that we were mining and mostly using in society. And in the last 20 or 30 years or so, we've seen that list of elements and metals, minerals expand massively. So lithium, rare earths, etc. I mean, lithium 20 years ago was only really used in medicine. Now it's an absolutely essential ingredient for the new renewable energy transition. And there's a whole bunch of other metals that are essential for modern technology going ahead. And so not only do we have these other metals that we're still going to need increasing amounts, we've got this whole extra set of metals that suddenly we need to get resources of and mine in increasing amounts. And it's a very dynamic field. And if you could predict the future and know what metal was coming next, you could make a lot of money. But it's obviously going to be more metals that we need. And I've got a couple of examples of things there. So natural radionuclides at the moment, radionuclides that we need for medicines, for cancer treatments, for example, they're pretty much exclusively made in particle accelerators, which is very, very expensive. And yet we probably have plenty of natural sources of these that hasn't really been looked at in uranium ore deposits, for example. So that could be a potential target for the future. Iridium I've listed there. That's a major metal needed for catalysis in hydrogen production. If hydrogen industry takes off, we're going to need to find a lot of iridium from somewhere, and yet iridium is probably the metal with the lowest abundance in the continental crust of all of them. And then thorium as well. I mean, thorium is probably not a major supply issue for thorium because we have plenty of thorium from rare earth and uranium mining that we don't do much with. But if thorium nuclear reactors take off, which they look like they increasingly, we're going to need a supply of thorium coming on. And for sure, there's going to be others. What we do know is that we're going to need a lot of metal in the future. We need it pretty quickly. So we really need to have lots of tools to bring to the table to be able to find these deposits. And why geochronology? Why do we need geochronology, let's say? And I think it's fairly well stated in that sentence that at the top there, if we're going to really think about mineral systems, understanding mineral systems on a holistic scale, we need to know what sort of environments they form in and when they form to be able to predict where we can find more of them. Here's a couple of examples of doing this on a very large scale. So comparing episodes in Earth's history to which were particularly productive for producing ore deposits. So gold, for example, we see here lining gold deposits up with age, and we see it lines up pretty well with the assembly of supercontinents across the planet. The second example is showing you that rare earth deposits on a global scale, there is a big a cluster of deposits forming between about 2 and 1 billion years ago, and particularly some of the biggest deposits that correspond to the so-called boring billion period. And so, there are stories behind these, but these are sort of interesting aspects of how our planet has evolved through its history. But there are much more details at a regional scale where geochronology can be really important. For example, finding mineralized episodes in the crust, then we can look for rocks of similar age as an exploration tool. So this is from a paper that came out a couple of years ago, sort of summarizing dating techniques applied to ore deposits. And so this is a pretty big, messy table, which I usually don't like to put it in a big table like this into a talk, but I will run through this in a few different ways. So it's probably worth having a look at. And in this sense, really, I'm only focusing on the first column, which is the decay scheme, and the last column, which is the minerals that we can apply that to. And so that's what we've got, the tools we've got in the toolbox for dating. And the top ones there are really the ones that at the moment are only widely available in situ form. So the uranium lead and the thorium lead decay scheme. And most people are very familiar with these, particularly by far the biggest application of this is to dating zircons. But of course, we can do it on other things as well. There's a list there: titanite, rutile, bedelite, phosphates, cassiterite even, we can directly date, tin minerals, etc. They're usually pretty reliable, but there are limitations to these systems to ore deposits. Firstly, zircon, the most widely used one, is actually not particularly useful for dating hydrothermal ore deposits because zircon's pretty immune to being affected by hydrothermal fluids. It doesn't really see them. And in some of the other ones, it's quite easy to leach lead out of them. So these, as geochronometers, they can be upset fairly easily. So they're not so reliable. And I'll show you some examples of that. So there are limitations for these uranium lead, thorium lead systems. There are other ones I'll talk about later, but in situ is actually really important because increasingly important because A, it's faster and cheaper in general than having bulk dating methods that require a lot of lab work, a lot of dissolution of minerals, etc. And most importantly, with in situ techniques, you can keep textural control on mineral paragenesis, which is really important for understanding all systems. And I'll keep coming back to that one as well. All right, but maybe an example of that, how complicated all systems can be in terms of their age evolution and why the petrography, the mineral paragenesis is really important. is an example from Bayan Obo, which is the world's biggest rare earth deposit in China. It's been extensively studied for many, many decades, and I think it has only very recently been resolved what the age of this deposit is. And so this first diagram here on the left, don't worry about the epsilon neodymium axis, but it's age along the bottom. And this is a compilation of data trying to date this deposit, and you can see age ranges go from 1300 million years down to less than 400 million years. And so we've got 1 billion years of age history, and there's been a lot of argument about what's the age of Bayan Obo. So the real solution to this is by combining in situ dating with understanding of chemical processes that go on with these rocks, including the minerals that we're dating and the paragenesis. And I think the paper cited here by Lee et al. Did a very nice job of really resolving this. What they did is went in and did really detailed petrographic work looking at microstructures, microchemistry of the minerals, and seeing and relating that directly to in situ dating. So in this case, they were doing thorium-lead dating of rare earth phosphates. And what they found, essentially summarized in this diagram, is that the primary mineralization for Bayan Obo is 1300. And then over the course of the next billion years or so, there were a series of hydrothermal magmatic events that upset these systems. They cause lead loss to the minerals, they cause recrystallization. And so many of these younger ages are actually in part geological resetting of these minerals. And many of the ages are probably geologically fairly meaningless. But some of them would be recording the resetting events. And it was only through this combination of doing the in situ age dating plus that detailed petrographic, petrologic characterization that it could resolve this story. So that's a really important message here. That the in situ techniques are really important for allowing us to do what is the hard work, and that is resolving the geological histories of these systems through petrography studies. This plot here I put up just to show a bit of a history of in situ geochronological techniques, mostly related to uranium lead and zircon. And really it's the two techniques we've got available, widely available, ion microprobe, starting with the development of shrimp in Canberra in the early 1980s, and then later laser ablation ICP-MS. And this is, I've basically represented this by just looking up how many papers have been published using these techniques as a function of year, just as a demonstration of how they've been taken up globally, and then put in a few sort of key moments in their history. And we can see shrimp picks up quite nicely as it gets developed, but not everybody in the world can buy a shrimp. So it sort of has, there's only a limited number of shrimps and ion microprobes around the world doing geochronology. Laser ablation, when it was first sort of suggested we could do zircon dating by laser ablation, there were plenty of problems to resolve. And so there's a little bit of a 5 or 6 years until this really took off. And then laser ablation, you can see, overtakes shrimp because laser ablation ICP-MS instruments are much easier, they're much cheaper to buy, they're much easier to install, and they often end up giving you a lot more data for less cost and less time. Although often the precision is not as good as shrimp. They're both very excellent instruments. What you do notice here is that after that, there is a bit of there's not much, nothing new coming on the scene between about 2000 and currently. It's not quite true, as you see. That's the point of today's talk, really. So let's go back to here, where this table, we've got those in situ techniques, and it's not quite true that they're the only established in situ techniques, because we can now do, thanks to laser ablation multi-collector ICP-MS, we can do samarium neodymium in situ dating. This is dating via an isochron technique, because the minerals that take up samarium and neodymium we'll also take up the background levels of those, so we can't assume that the minerals are free of the daughter product when they form, unlike what we do commonly for zircon. But I've added a bunch of minerals on here. So anything, this is, if you have a laser ablation system with a multi-collector, you can do this fairly well. There's quite a number of labs around the world doing this. And anything with more than about 200 ppm neodymium, which is most rare earth minerals, you can date in situ now. And it also potentially gives you the initial neodymium isotope composition of that system as well. Keeping in mind, it is an isochron system, so you can't just date one mineral and get 1 point, get an age. You need a spread along the isochron to get an age. And I'm not going to talk any more about that. I've got some examples at the end if people are interested, because I want to move on to some of these other systems that we've been doing. Okay, and that's these ones. So what I'm talking today about are these so-called beta decay systems, where so rhenium to osmium, rubidium to strontium, and lutetium to hafnium. And classically, these are incredibly difficult to do on a mass spectrometer, because if you look at those systems, the parent and the daughter isotopes have the same mass. Hence, that's the beta decay systems. And so for a mass spectrometer, which just measures the mass of the analyte coming in, it can't resolve two masses which are, well, the same mass. So for a mass spectrometer, it can't tell the difference between a standard mass spectrometer between 187 rhenium or 187 osmium. And so that means the classic way of using these techniques is to do fairly complicated. So firstly, you pick out your mineral of interest, and then you have to do fairly tedious wet chemistry methods to separate the isotopes out into different portions and then measure them separately on a mass spectrum like a TIMS or a multi-collector machine. And when we do that, and so those techniques are fairly well established. Rhenium osmium dating of moly, for example, molybdenite is pretty much the standard approach for dating many sulfide-rich ore deposits. But it is time consuming and often takes, for a lab to do this can take 6 months or more. It's expensive. It's a lot of time for technicians, etc. And importantly, it requires removing the mineral from its geological context. So you've got to pick it out of the rock and then dissolve it up. And often you're doing the whole mineral. So you don't know if there was internal zoning or complexity within that mineral. You're not going to see that with the end result. It does give you very, very precise results, however. And that's also true for the other systems, rubidium to strontium and lutetium hafnium. I would put out for lutetium hafnium in this particular paper, they're only mentioning that this is applicable to garnet. And what I'll show you today is that's completely untrue. All right, so what we can do now is that we can do these systems in situ by laser ablation. And that's really what the game changer is today. How do we do that? Well, it's basically possible because advances in the mass spectrometry side of things. And so the instrumentation has been around for a little while, and really it was only in 2016 where the first paper came out that sort of suggested that this may be applicable to geological systems. And that paper is this one, in Chemical Geology 2016 by Thomas Zach and Hogmal. And in fact, Thomas Zach has really been a pioneer of developing these dating techniques, and many of them. And it's particularly good for these beta decay systems where you don't see a change in mass between the parent to the daughter isotope. It's just, as you can see here, it involves loss of electron only. And as the title says, the dating requires online chemical separation of rubidium and strontium in a reaction cell. And so the way it works, and there's a little cartoon here to show you how it works with modern mass spectrometers. So an ICP-MS usually has something like a quadrupole on the back end. That is your filter for separating out your masses before it goes to the detector at the end. The most ICP-MS instruments these days don't just have a single quadrupole. They have what's known as a reaction cell sitting between two quadrupoles. And this is a cartoon for the Agilent system, which they're calling a triple quad, the QQQ. But how these work is we have our masses. We've already ionized our material, however that is, with laser ablation introduction into the ion, into the plasma torch or by solution. It comes in to the back end of the instrument, which is what's shown here. So these are ionized analytes. So in this case, we're looking at 176, which could be lutetium, it could be ytterbium, or it could be hafnium. The first quadrupole basically filters everything out except for what mass 176 in this example. It then goes into the reaction cell in the middle of the diagram there. And in this case, we're putting in ammonia. And the neat thing about ammonia is it reacts only with the hafnium to make this very complicated polyatomic molecule here, but it does not react with the lutetium. And by doing that, it actually shifts the hafnium mass to a new mass, in this case, mass 258 instead of mass 176, because it has all these extra atoms from the ammonia on it as well. And that by doing this, we're actually tricking the mass spectrometer thinking that the hafnium is actually a different mass. And then through the second quadrupole, we can actually sequentially filter out which mass we want to do. If it's the 176, it's going to be the lutetium. And if it's 258, it's the hafnium component that we detect at the end. So it sounds like kind of something that's nice in theory, but in practice should never work, but it actually works amazingly well when you get it, when it's set up and operating well. So that means we can now measure both the parent and daughter isotopes of these beta decay systems. And so rubidium strontium is probably the one that's been developed the most. It's actually, it's been applied in many labs now all around the world, and it's applied to things that have high rubidium content. So these are micas like muscovite biotite. We're working on refining lithium-rich micas at the moment, which is doing quite well. Feldspars are developing, and you can even do bulk rock samples like shales by doing a big spot on a shale sample. And there are a whole bunch of papers here. I've just listed a few of them that document this, but there's been a lot of work here in Adelaide applying this, and the folks in Curtin have been doing this a lot as well. Something that is probably, I think it's safe to say, fairly exclusively developed here in Adelaide is lutetium hafnium dating. I'll talk quite a little bit about that, and that was really the focus of Alex Simpson's PhD from a few years ago. And there are a whole range of minerals that we can apply that to. Anything with a few ppm lutetium, we could apply this to. And you can see the minerals there. Many of those have applications directly to ore deposits as well. And then lastly, rhenium osmium for molybdenite, which is, of course, the sort of the industry standard for dating ore deposits. We can now do that in situ as well, which is really, really neat. And so we've got a recent paper out on that. And I've put pyrite there because we, in some cases, particularly for rhenium-rich pyrites, but they have to be very rhenium-rich, we can date pyrite directly as well. Okay, so on to some examples. Let's start with the lutetium hafnium. We want lutetium-rich minerals, and probably if you know much about metamorphic rocks, garnet is probably the easiest example of a mineral with high lutetium content, high heavy rare earth content. So we started with looking at garnet. Can we date garnets using lutetium hafnium in situ? And the simple answer is yes. Here's some examples from Alex's work where we took some garnets of known age and analyzed them in situ to see if we can reproduce their age by lutetium hafnium isochrons. And so we've got three examples here. The top one here, I think this is an eclogite from Tanzania or somewhere in Africa. The published age is up the top here, 1994 million years ago. And the isochron, you can see there is 2046 plus or minus 62. So within error of the established age, although you can see the uncertainty is relatively high in comparison to other techniques. The second one is an eclogite from Port Macquarie. Should be 490 million years, and we get 481 plus or minus 23. And then the third example here is from the Western Gneiss region in Norway, and the isochron gives 1060 plus or minus 35. This is the Garnet here, the panel G here. And for that isochron, we're just looking at these high lutetium ones in the core. So that's the little green dots, that's the laser spots. And this Garnets also have monazite inclusions in them, which have been independently dated at 1055. So the Garnet age is replicating the monazite inclusion age. So it works quite well for Garnets. So not just for raw deposits, obviously for understanding metamorphic rocks, particularly when you have complex zone garnets, this can be really powerful for pulling apart the temporal history of metamorphism. Apatite is a very nice mineral to use this with. Apatite, we can also do uranium lead dating. That's being fairly well established now. And so this is this particular application here, or this example here, was to see how the lutetium hafnium dating of apatite compares to uranium lead dating. And so for this work, this is a Stain Gloria's paper. He took a granodiorite sample from South Australia, south of Adelaide here, that has a very well-known igneous age of 497. That's this Tim's uranium lead age here. And then looked at dating this particular sample with various different techniques. And the top two panels here show you the apatite geochronology. The first one on the left is the uranium lead age, and uranium lead in apatite rarely, quite often doesn't plot on Concordia. There's often quite a lot of common lead in there, so we get these arrays. But if you project that down, you get an age of around 440 million years ago. So a fair bit younger than the crystallization age, but that does correspond to sort of a known regional hydrothermal event as well. But if you look to the panel to the right, you see that's the lutetium hafnium. This is an inverse isochron here. The lutetium hafnium age is spot on the age of the crystallization age of 500-ish. And so that's really telling us that in this case, the apatite is recording the primary igneous age, and the uranium lead age has been reset by a later event. And so it looks like lutetium hafnium may be much more robust for the primary age. The other two plots here are just some additional data for the monazite, which also came back at 500. And this plot here is is titanite, which actually records both ages. But really the take-home message here is it looks like that apatite is better at recording primary ages than the uranium lead system. And so to follow up on that, this is work by Melissa Karkongo here at Adelaide. They wanted to test this a bit further with some other mafic rocks in particular. Mafic igneous rocks can be quite challenging to date because they often don't have zircons, but they often do have apatites. And so it's three case studies we're looking at here. The first one from Sudbury, which is the well-known meteorite impact in Canada, and took mafic rocks, so these are diorites and gabbros, and then dated them by uranium lead and lutetium hafnium, the apatites. And the other two examples were from orogenic zones where there is mafic magnetism associated with orogenesis. And so the little green box is the period of orogenesis, or the impact structure for Sudbury, with the ages of some of the mafic rocks in that area. And we see for Sudbury, both uranium lead and lutetium hafnium come out pretty much the same age, and that corresponds very nicely to the age of the impact. But when we look at the orogenic systems, in both cases, we see that the uranium lead ages are significantly younger than the lutetium hafnium ages. And it's the lutetium hafnium ages that correspond much better to the original orogenic ages. Again, looking like the lutetium hafnium is recording the primary igneous age, and the uranium lead is being reset by later events. So that's pretty neat. So a very good complement to uranium lead in this case. So that's apatite. On to carbonates. Calcite is now possible to date that directly with lutetium hafnium. It's a little bit more challenging than the other minerals because calcites often don't have high lutetium contents, but it is feasible. Here's a couple of examples. The top one here is the Palabora carbonatite, which is known to be 20-50 million years old. It's a known copper deposit. You can see the sample here with chalcopyrite and igneous calcite. This map here is this false color image of a mineral map collected by MLA, or sort of automated mineral mapping, SEM-based mineral mapping procedure. And so we've got chalcopyrite, or sulfides at least, in this sort of tanny color, this bronzy color, and the carbonates, the calcites in pink and dolomite in blue. And the little round spots are the laser spots. They're about 200 microns in diameter, so quite large laser pits. But here's the isochron we get from that, and we get an age of 2064 plus minus 30. So again, it's working very well for carbonatites in this case. The second example is a skarn from America. This is from the Mount Elliott skarn in the Mount Isa inlier. Sorry. Oops, I'll go back. And there's a vein cutting through this skarn. It has calcite in the pink here, with andradite garnet in the blue, and there's also titanite and apatite in here. It's been previously dated to be 1540 million years old, and the calcite here, you can see the age here, it's 1540 again. So it works quite nicely for calcites, provided there is enough lutetium in your calcite. And that's sort of shown here. This gives you an idea of the sort of precision that you might expect based on the composition of your calcites. So these are all calcites, and in brackets here is the age. You can see they're all Proterozoic. This is obviously this is a radiogenic system where you're relying on time to build up a certain concentration of the daughter, and so lutetium hafnium is quite a long-lived system. It has quite a long half-life, so it's quite challenging to date young things. And you can see the age here. These are all Proterozoic. It's very good for Proterozoic things because you've got enough radiogenic hafnium build up to be able to measure it by the mass spec. And you can see here's the lutetium content of our calcites. When we get below about 2 ppm, you can see the uncertainty blowing out. This is uncertainty on individual data points, by the way. Getting up to 10% when we get to these very low levels, just because our signal that we measure on the mass spec becomes very low as well. So ideally, we want calcites with more than about 2 ppm, and we get sort of fairly reasonable precisions on the analysis. And so that clearly indicates that it's good to screen your samples before jumping in and thinking we can date them. We need to get these ones with high lutetium contents. But that, this is ideal for Proterozoic and older samples, but we have dated things down into the Cretaceous, for example. It is possible if the sample is right for that. Right. Other minerals, fluorite. So fluorite obviously is a very common mineral associated with many ore deposits like IOCGs and skarns, etc. Fluorite is difficult to ablate by laser ablation, but modern lasers can do it. And in this example, another one of Staines' papers where he wanted to see whether we could do lutetium hafnium dating of fluorite. He's got a sample here of a hydrothermal vein from the Olympic Dam domain. So in the map here, you can see Olympic Dam here, and this is from this drill hole over here, TD2. So the geology tells us this fluorite should be the same age as the IOCG systems in the Gawler Craton, which is all around 1590 million years ago. And indeed, that's what they got from dating the fluorite. So here's the isochron, the age down here, 1588. So fluorite's possible as well. And the second one is just showing the coexisting calcite. If you consider that on its own, it also gives the right age. So we've got two minerals there that we can date, giving the age of the hydrothermal system. Okay. And more recent work they've done is shown that it's applicable to apatite group minerals as well. And I'm sure there'll be more applications coming in the near future. So that's lutetium, hafnium. On to rhenium, osmium. This probably will be quite a lot of interest, particularly to industry, because the classic way of dating rhenium osmium, moly by rhenium osmium, is quite time intensive and cost intensive. But we've been working to see if we can do this in situ, and we've been testing particularly whether we can develop standards, which is this new paper by René Tamblin has actually sort of documented two standards that are now available to do this in situ. And these are molybdenites that come from Merlin, the first two here, which has a known age of around 15, 18, 15, 20. These plots here are really just to show the reproducibility of the analyses. So the precision is pretty good. And using these two materials as standards, we can now date, we've shown through this paper, you can date other mollies of unknown age fairly accurately. And that's also shown here. So this is a plot just showing age of our analyses, which are the pink bars here, versus ID TIMS, which is sort of the classic traditional way of doing rhenium osmium dating, either the ones that we've done for our study or ones that have been published in the literature already. And you can see in all cases for these 5 different mollies, we can reproduce the age within uncertainty. What we do see is that in most cases, the laser ablation data has a significantly larger uncertainty than the ID TIMS. It is an in-situ laser blaze technique, which is pretty common, that you'll have a larger uncertainty. So while this is much cheaper and faster, it is important to realize that the uncertainty on the age will be larger as well. Okay, and in terms of the sort of detection limits we can get here, this plot here is showing, this is sort of contoured for the rhenium content as a function of time, because rhenium will decay to osmium through time. And all the little black dots behind here is a global data set for molybdenites geochemistry from Barton. Anything above about 10 ppm rhenium here gives reasonably good uncertainty on the order of a few percent. And you can see that anything above that line, that's a lot of, most of the world's molybdenite should be doable by this technique. But if you have very, very low rhenium, then you're going to have very low osmium, then maybe this isn't the technique required, but that's only probably a minority of natural molybdenite. Yeah, so we have those standards available. If anyone's interested, I can send them some samples of those standards to do that. All right, so how are we going? A few more minutes. I probably to finish up with a bit of a case study for an IOCG, and then I want to show you a pretty cool application that's been developed here, sort of improving the textural and the paragenetic link between geochronology and our samples. So this is a bit of a case study where we can apply multiple of these new dating techniques to unravel what is a fairly complicated temporal history in an ore deposit. So Vulcan, it's in the Olympic Dam domain. It's just north of Olympic Dam. If you look at this middle panel here, here's Olympic Dam, and we're about 20 kilometers to the northeast of Olympic Dam. Vulcan is actually a magnetic anomaly. We can see here, it doesn't outcrop, but there are a number of drill holes into it to see if this is an IOCG system, and it is an IOCG system. It's just, it hasn't got particularly a lot of copper, unfortunately. but it's a nice place to do a case study at least. So here's some of the samples that Alex Simpson worked on to try and unravel the geochron. So the first one's here. These are some of the core images of the sort of iron oxide sulfide rich breccias, and the colored images are these false color images of the minerals that make up the samples. In these top panels here, the red is the iron oxides, and the sort of tanny, I don't know, orangey colors are the sulfides, mostly pyrite. And then there is quite a bit of apatite in here, and carbonate, siderite, calcite, and dolomite. So that's sort of the primary ore, let's say, highly brecciated. And then there are samples that have these cross-cutting dolomite veins we can see on the right, clearly later, and they do have some chalcopyrite and carbonate in them. And there are also more complicated samples that have things like bastnasite, which is the rare earth fluorocarbonate. And so lots of potential minerals to date with these new techniques, which is what Alex has done. So here's some of the results. There's moly in there. Here's four samples of moly that came out. In this case, we're not showing the isochron. These are just the weighted mean plots. And they all come out 1600-ish or 1590-ish. So pretty much the age of Olympic Dam, the primary age of Olympic Dam. The apatites also, this is the plots on the left here for apatite, the uranium lead plots, and you can see they're a complete mess. So the uranium lead system is completely mucked up in this system, but the lutetium hafnium system holds together quite well. And again, we're getting these 1590 ages out of the lutetium hafnium in the apatite. So that's nice. And then the story gets a little bit more complicated once we start looking at the carbonates. So this paper, I think it's probably the first time ever that dolomite and siderite have been dated in situ, and they give a range of different ages. Some of them will give the primary age of 1590-ish, like this one here on the right, and then many of the others gave much younger ages, down to, you can see this one here, 330 million years ago. And so if we put all that together in a sort of a summary diagram, this is now looking at IOCGs across the Gawler Craton, with age on the vertical axis up through here, and the symbols are color-coded by which mineral was dated. And we've got various ore deposits along the bottom: Prominent Hill, Olympic Dam, Acropolis, here's Oak Dam, the new one that BHP are working on, Carrapateena, and so on. And then our data for Vulcan are in this last plot here. Sorry. And if we put all that together, we can see obviously the most data there for Olympic Dam, but even from this one study, we've actually now Vulcan has the second most data in terms of its temporal history. And Olympic Dam has this long history. The primary age of 1590, you can see that's reflected all the way across here, corresponding to the Hilltop suite, well known in the Gawler Craton. Vulcan also preserves that age, but there are younger ages. There's something coming in here at 1450, which we also see in Vulcan, and there are a series of other ages reflecting later orogenic episodes that are actually affecting the continent at quite some distance from the Gawler Craton, but are still being recorded by these IOCG systems, which is quite neat. And the difference is this can be collected once you have that petrographic context. All of this geochronology data can be collected very rapidly as an in-situ technique. All right, my final example is just to show you something else very neat that's people here have been developing, particularly Darwin Subaka here, the postdoc at Adelaide, and that is combining mineral maps with geochronology. So he's developed this for uranium lead, and I'm going to show you an example of this applied to the rubidium strontium system. So this is an example from the Lochlearly Cars belt, which has been a bit of a focus for surveys and GA for a while, and also Minex drilling program, because it is a pretty much completely concealed belt of rocks, probably possibly continental arc related, that may have, for example, porphyry copper mineralization potential. And so there's very little previous work on this. What previous geochron work has been done was this paper by Batar et al., where they dated a couple of the intrusions that came up in the drill core, and they got ages of 496 MA and another age of 393. So keep those two ages in mind. And this work I'm going to show you is on this particular drill hole from the Minex program. And this is the sample here. It's an altered granite sample. It looks pretty messy here, but what we've got here is a laser map of a section of a thin section of this material. It's over about 1 millimeter wide by something like 5-6 millimeters long. And the colors represent different minerals, and they've been, in this case, we've picked out 3 different elements to represent the colors: calcium, lithium, and rubidium. That's just the elements they picked to highlight the different minerals. A few things we can see in this thin section. Firstly, over here, there's a carbonate vein, the high calcium here. That's obviously clearly hydrothermal coming after the granite, and that's yet to be dated. That's probably work that Darwin will do soon. And but the interesting part for this talk is over the other side here, this lithium-rich material, probably not particularly lithium-rich, but lithium is good at picking out the feldspars in here. And the greeny color stuff, the high rubidium, is micas that are texturally quite late. They're coming in, they're infilling late spaces. And so the neat aspect about this mapping tool is that once we have this map, we don't have to go back and re-drill all of these minerals to get the geochron. The tool that Darwin has set up here is you can actually integrate each of these pixels on the map and directly plot them to get ages. And so that's what he's done here. In the first instance, he's taken all of these sort of light blue domains, the pixels from those, and plotted the data to get an age. And that's this here. So that's the lithium-rich feldspars. It's nearly 100 data points here. And we get an isochron age here of 486 plus or minus 8. So that's agrees very nicely with that previous dating result that was from uranium, lead, and zircon. We do the same little trick with the late stage lithium mica. Here's the data, a little bit of a larger uncertainty here, but 363 plus or minus 40 is within error of that 390 age that was determined previously. And so this is a really powerful tool to directly link mineral maps, petrography to geochron. And I think this has a bright future ahead for lots of applications. All right, my time's up. I better wrap it up there. So really take homes, I think these development of these beta decay geochronology systems is really going to be a game changer for geochron. It's not going to replace other geochronological tools. It's just going to complement them and allow us to unravel the development, the formation, the development of all systems, as well as many other geological systems. And I sort of ran through a lot of these. There are a couple of others that are possible to use that we don't need to mention here, but this is still in development. So one of the biggest limitations we have is standards, and we do need to develop standards, matrix match standards, and we are working on that. A number of labs are working on that. And the other thing I will highlight here is that this allows us to do in situ approaches where we can link geochron to mineral paragenesis, but I'll turn that around to say that with this data, to really understand what it means, it's the petrography and the paragenesis that is really essential to get that nailed down before you start to think about what these ages mean, because as we've seen those last couple of examples, you can get a range of different ages on within a single sample. Okay, I'll leave it there, I think.
Yeah, that was a really fantastic session. So thank you so much, Carl, for getting involved. And yeah, I hope everybody enjoyed themselves.